Hi everyone, in the earlier video we had prepared the maze for both conical and tangent ogive nose cone, and in this video we will do the physics setup and run the simulation. So now go to the component systems and find CFX and drag it to the work area and drag the maze to setup. Now after that we will have to re-update the maze. Right click and click update. So it will take some time. I will pause the video. So the meshing is updated. I will also rename this name CFX as conical CFX. Right. So now double click the setup to open CFX-Pre. So it's opening. I will make it full screen. So inside the maze is already loaded. You can see A's on the top of the nose cone, because it has a pointed A's and it was not properly resolved because of the coarser maze. So let's ignore that for now. Now we need to set up the simulation. So inside analysis type, keep steady state as it is, because we're going to perform steady state simulation. Okay, and then now right click on default domain and insert a boundary. So the first boundary that we want to insert is inlet. So we see that the boundary type and location are already selected for the boundary inlet. It's because I gave the same name previously. If it's not automatically selected in your case, select the boundary type as inlet and location as inlet. Now go to the boundary details and give the normal speed as 200 meters per second. So the velocity 200 meters per second is about 0.6 Mach number. Press OK. So again, right click on the default domain, insert boundary, and type opening. So again, the boundary type and location are already selected. In this, give the relative pressure of 0 pascals. So it means that it is an open type of opening. I suggest you to read about boundary conditions, including inlet, outlet, opening boundary condition. So maybe we can also include this in some of our later videos, but not in this one. So click OK. Now after that, again go there and insert a boundary. So keep this name as nose cone. So the location is already selected at nose cone, but the boundary type is not inlet, it is a wall boundary condition. Inside boundary details, leave as no slip wall, since it is a no slip wall. No slip wall means at the wall the velocity of the fluid is 0, and also give the wall roughness option as smooth wall, because for now we do not know the friction values and friction coefficients. And click OK. And apply the similar condition for the body. So first notice that there is a default domain default, which means that this surface is not selected yet. Now if we go here and insert a boundary condition and give it a name body, we can give any name as we want. So the body is already selected, this is also a wall, and we keep the same settings as there already is. Okay. So notice that the default face is not there now. So we have applied all the boundary condition now. It is a pretty simple physics setup. Now let's go to the solver control and let's increase the maximum iterations to 500, and let's leave the convergence criteria of residual target of 10 to the power minus 4. So these values of maximum iterations and residual targets should be understood properly, and they should be calculated properly for accurate solution. For now, let's leave the residual target of 10 to the power minus 4 as convergence criteria and 500 as maximum iterations, and click OK. Now go to the expression, right click, insert an expression, and type drag force. So it's just a name, you can give any name that you want, but you cannot give the name that is already used in the software. For example, you cannot give pressure, you cannot give inlet and such things. So here right click and click functions and click locator based and click force. Okay, I'll let you know what I'm doing right here. So after force, type underscore, type X, and after at the rate, go to right click and click physics locator and 2D and select NOSECONE. So what this expression means is that we are trying to calculate force in X direction that is applied at NOSECONE. X direction because the axial direction of the rocket is X direction. So this expression will give us the value of drag that is caused due to the NOSECONE applied. So we close this. Now what we can do is we go to output control, then we go to monitor and we select monitor objects. This is used to monitor some values during the simulation, so we can see what the value of certain parameter is while the simulation is still running. So click this button and leave the name as monitor point 1, and inside the option select expression, and the expression value right click expression and select the drag force that we just set up. So this monitoring is actually not necessary in our case because this is a steady simulation and we can later find out the steady value from CFX post. I'm only including it here so that we can learn how to use monitor points in ANSYS CFX. Click OK. So now we are done with physics setup. Now let's save this file and let's exit CFX-Pre after the saving is done. Close CFX-Pre. So after that, double click the solution. So the solution has opened. Click the double precision, and based on your computer you can use parallel processing or serial processing. I'll go with serial processing for now, and in initial values leave it as it is. After that, go and click start run. So this is going to take some time. After the running starts, our monitor point will also show here, which is the drag force in our case. This might take some time. I'm not sure, like if it reaches the convergence criteria earlier, it won't take much time. If it does not reach the convergence criteria, which is 10 to the power minus 4 in our case, it will just go on for 500 iterations. So the user points will also be plotted here, which is drag force in our case. The convergence residuals are pretty close to 10 to the power minus 4, so I think like this solution won't take much time. So I will pause the video till this solution is completed. So the simulation is complete in less than 20 iterations because all the residuals have gone below 10 to the power minus 4. That was our criteria, so we would have like made this criteria a bit more strict, but this is fine. We can also see the value, the monitor point, the drag value, that it is also converged somewhere around 8 Newton. So we can calculate this value later on. So the simulation is done. So let's close this, close CFX Solver Manager, and let's save the file first. And I have also performed exact same case setup and simulation with tangent ogive NOSECONE. You can see it in the screen. So in this video, we performed the physics setup and CFD simulation of both NOSECONEs. And in the next video, we will visualize the results and do the post-processing in CFX Post. Thank you and see you.